Mason Kamb from Stanford, and he's going to present an analytic theory of creativity.
Yeah, all right. Hi, everyone. I'm Mason Kamb. I'm from Stanford. Yeah, I'm going to be talking about, thank you for giving a lot of introduction about diffusion models. I'm also going to be talking about sort of a similar kind of notion, but we're going to be studying it in convolutional neural networks. And what we're going to be able to find is a theory that is able to predict on a point-by-point basis the outputs of these diffusion models as shown here. This is joint work with myself and my advisor, Surya Ganguly. So I think the basic kind of phenomenon that we really wanted to explain in this work is the phenomenon that diffusion models seem to exhibit what you might call combinatorial generalization or combinatorial creativity. This is the phenomenon that these models seem to be able to kind of promiscuously mix and match elements that could really only be represented in different examples in their training set in ways that don't look like just simply regurgitating memorized training examples. So these things on the right are examples of this phenomenon from DALL-E 2, where you see different attributes that could plausibly have been represented maybe once before, but not across all possible combinations. These combinations are always, or generally speaking, quite novel, but still show qualitative consistency with attributes that you see represented in the training data. And so ultimately what we're looking for is a theory that makes these properties as manifest as possible. Now, of course, I said that these generations are consistent, but of course this is not guaranteed. Famously, diffusion models are really prone to generating things that are spatially inconsistent, like showing hands with too many fingers, showing too many teeth and mouths, showing text that looks completely garbled. Some examples of this I'm just showing here. And what we're going to argue today is that this kind of phenomenon of combinatorial generalization, creativity, and inconsistency of this kind are actually on a spectrum. And we're going to be able to identify a single mechanism that explains both of these phenomenon in quantitative detail. OK, so I don't have to go through this in as much detail as I thought I might. But so yeah, diffusion models, basically the idea is you start with some training set. You generate a bunch of corrupted examples by adding noise to these training set examples, or interleaving them with Gaussian white noise. This interleaving is sort of equivalent to running a particular SDE on the data distribution. And the idea is that we'd like to kind of go in the reverse direction from the noise back to the signal by running a reverse process. You can do this stochastically or deterministically. The point is that it should capture the evolution of this probability distribution across the sort of the noising time. And so in this case, what we're going to do is we're going to just take samples from the Gaussian white noise and then evolve them under this vector field here. This vector field here has an important term. This important term in the middle, this grad log of pi of t, is the grad log of these intermediate noised distributions here at each time. And this is called the score function. And what makes all of diffusion modeling possible is that there is this identification between the score function and the conditional estimate, or the conditional expectation value of the added noise given a particular corrupted sample. So this is saying that if I am looking at this image here, this corrupted image, my best estimate for the noise given that image should be proportional to the score function. And this motivates the training objective for these neural networks, which is simply say, give the model a image of this form and say, OK, produce for me your best estimate of the noise. Guess the noise as best as you can with a squared loss. And if it is able to do this perfectly, it will compute the conditional expected value of the noise given the corrupted example. However, there's a bit of a problem with this, which is that if you do this perfectly, this is mathematically guaranteed to reproduce the statistics of this distribution, or of these noise distributions as you run this process. And unfortunately for us, as we take this all the way back to time equals 0, the distribution that we'll be recovering is the sum of delta functions on the training set. And that corresponds exactly to memorized samples. So this is really bad if you would like to see a theoretical production of something like combinatorial generalization. So essentially what this is telling you is that in order to avoid memorization, diffusion models are underfitting their training objective, and we should try to understand what the implicit biases and constraints are that prevent it from fitting this. So the approach that we took was to study this in really the simplest realistic diffusion model. So this is a diffusion model parameterized by a fully convolutional neural network. Most diffusion models today actually are almost this, but they have additional layers, self-attention layers that are kind of, effectively like the cerebral cortex of the model. But we study it without these layers. So we've done a little bit of lobotomy, a little bit of brain surgery in order to get a more tractable setting. Just by the way, this is actually the same architecture that was used in the very first diffusion model paper in 2015, which was before the kind of the attention renaissance. Okay, so in general, convolutional neural networks are extremely expressive class of models, but they have two constraints that are really important for us. The first of these is translational equivariance. So this is saying that these models if you translate the input to these models, the output gets translated equivariantly. And then the second one is that they seem to have some inductive bias towards locality. So for us, locality means that if you consider any given pixel in the output of one of these models, the value that the model produces at that pixel location can only depend on a small or medium or even large, but a fixed kind of local region around that pixel. So it can't use the entire image in order to form its output at any given point. And so these two constraints are actually, they are not satisfied by the optimal denoiser, and so it's reasonable to ask, okay, what is the optimal denoiser given these two constraints? Okay, so first of all, let's sort of ask, okay, what is the optimal denoiser? This is the same thing as the empirical score function, and the basic idea is that it's just simply asking you to, in order to guess the noise that you've added here, you say, okay, what are the possible images that could be living under this noise? And I'm going to average the added noise that I would need to have to go from that training set image to the corrupted image that I see currently, and then weighted by the Bayes factor for that training set image. And this is just saying, okay, what's the likelihood of making this noise jump under the noise model? This is added Gaussian noise, and then divided by the sum over all possible training set images. Now, when we impose locality, this is going to be almost exactly the same thing, except for this Bayes weight here for this ideal score function is a global function. And what happens when you impose locality is now each pixel gets its own Bayes weight. So each pixel now is computing a Bayes weight that says what is my belief about the training set image based on what I can see in my local context only. So there is a decoupling of the beliefs across the image, and each pixel is effectively like a little agent that is doing its own denoising on its own time. Now, when you add equivariance, this is equivalent to deleting a pixel's knowledge of its location within the image. And so the optimal equivariant local denoiser is given simply by augmenting the data set with every possible translet of every possible image in the training set. But otherwise, the formal expression is almost exactly the same as in the ideal denoising case. So just schematically, this is the cartoon you should have in mind. This is optimal denoising. Every pixel shares the same global weight. You move in lockstep towards a memorized training set image. This is optimal local denoising. Each pixel has a different weight. Sometimes if they're very far apart, they can be completely uncorrelated. And they move towards the images that they most believe that they came from, which may in general be different. And then when you introduce translational equivariance, now you can actually mix and match images or parts of images that are represented in different parts of the image. And again, so key takeaway here is that the kind of formal mechanism that gives you combinatorial generalization or combinatorial creativity is this kind of effect where you've decoupled the beliefs, and then as you denoise, the pixels move towards the values that are in the training set for the images that they most believe that they came from. And this just automatically forces the model to mix and match attributes while retaining local consistency based on the sort of the locality scale. So again, this is the essential mechanism. If you can remember nothing else, this is the point. More formally, so the kind of the generated samples that you can get satisfy a particular constraint, which is that at the end of the generation process, the center pixel of each patch should look like the center pixel of the L2 closest patch in the training set. So it doesn't need to agree over the entire patch, but there should be some kind of local consistency embedded in the generation. And here I've shown just a schematic of this. You go from this data, and then you get a bunch of points that, a bunch of samples that kind of look like this. But no samples that look like this, which have these sort of violations of these constraints. This is a formal result, but it kind of helps you intuit how this mechanism gives you kind of a combinatorial explosion of new samples. Okay, so does this work? So we trained two architectures, a 6-layer ResNet with sort of narrow convolutional filters, and then a sort of larger 3-scale UNet on 4 standard computer vision data sets, MNIST, which is handwritten digits, fashion MNIST, which is fashion articles, CIFAR10, and Celeb A, and then we compared on a case-by-case basis the outputs of our theoretical model to the outputs of the trained diffusion model, given identical input noise. And so this is just kind of an example of the results that we can get. So each of these are pairs between the theory and the experiment, and you can see that they match very, very closely on a case-by-case basis. Just to kind of show you more examples of this. Again, you can see that this is quite high fidelity, although the quality of the samples are not excellent. Faces in Celeb A. This is quantitative as well, so the correlations are all almost all at about 90%, and then there's like 1 or 2 that we didn't quite manage to get above that. But it's to our knowledge the highest theory experiment correspondence across any class of deep generative models. The theory predicts spatial consistency issues. So in this case, you can see that these are supposed to be fashion articles. So we've got like a set of pants that have too many legs, shirts with too many arms, etc. And the mechanism for this is very simple. When you have a locality constraint and a pixel is deciding whether or not it should become, say, e.g. a pant leg, it cannot count the number of pants in the image. And so the number of pants you get is just stochastic. And you get just randomly things with too many pants. And then we hypothesize that this is sort of more general than this. Okay, so how much time do I have? I've got like a few minutes. So going a little deeper, so I didn't actually tell you what the locality scale is. And so we actually had to fit this. This is a free parameter in our theory. And what we find is that the neural networks seem to use a coarse locality scale at the highest level of noise, and then it kind of reduces throughout the generation process. There's a motivation for this from the sort of question about sample complexity and memorization. If you know about the dynamical regimes of diffusion by Biroli, this is basically allowing you to surf above the memorization threshold all the way down to 0 noise. Okay, oh yeah, so we also trained this, we tested this when we added attention back in. One of the things that we found is that on a case-by-case basis, these are very close to each other. So these are the bottom rows here, or the bottom pairs here are the theoretical predictions on a given input noise, and the top row is the attention-enabled model on the same input noise. And you see that they're very close to each other, but the attention-enabled model is somehow able to carve out a semantically coherent foreground object from what the local model produces a textural background kind of thing on. So there's some kind of sense in which these two things are related, but the attention-enabled model is a little bit smarter about what it's doing. We also find that there's evidence that these kind of spatial consistency issues in the attention-enabled model actually carry over from the local model. So here I've shown an example where this is supposed to be a dog. The local theory just predicts like this thing here, which is not really interpretable. But the self-attention-enabled model produces something that has the features of a dog face, but it's got 3 eyes, or maybe even 4. I can't tell exactly. And so I picked this cat image off of the internet, but this is kind of an example where I think qualitatively these two kinds of generations are similar, and we hypothesize that the mechanism involved in both cases is the same, that it's somehow derived from this kind of locality bias that persists even when you have a non-local module in the network. Okay, so I think, closing thoughts. We've been able to give a theory that is remarkably predictive for the behavior of an inattentive convolutional neural network diffusion model on small data sets. This theory exhibits this kind of promiscuous combinatorial generalization recombination effect. By default, it follows automatically from the math once you impose a locality constraint. It is as far as we know to this day, it's the highest theory experiment correspondence for a class of deep generative image models on standard computer vision data sets. And although this is sort of restrictive, it's not the state of the art. We have kind of some tantalizing evidence that the effects that we find seem to inform the ways that more complex models operate. So thank you.
Very nice. Thank you, Mason. There's the questions.
Thank you. Very cool work. And I was wondering, because you showed that there are cats with 3 eyes in both the convolutional network and the model with attention in it. So there are 2 models with or without locality, and they both have this issue. So I was wondering if this kind of consistency is not coming from the architecture.
So I think the interpretation that we have of this is that the attention-enabled models are still using sort of local data, but they have like some kind of minimal kind of non-local control over what's going on to kind of bias it towards a little bit better global consistency. Recall that sort of local denoising is a good heuristic because in reality, pixels in natural images are very correlated if they're very close by. So if you attend locally, that's a kind of a good thing to start with, and then you have the ability to look over a kind of a broader window, and so you start to learn like non-local correlations that are useful. But so that's kind of what we think is going on with the self-attention enabled models. We don't know exactly what kinds of correlations enable them to kind of get these sort of more coherent, semantically recognizable objects. But we think that they're in a case like this, it's probably kind of learned some intermediate amount of global correlations, but not sufficient to kind of correct this effect that seems to trace its origin back to the local model.
Okay, thank you.
Thanks for the talk. I was wondering, since you said that this kind of like wrong number of eyes or wrong number of legs depends on like 2 local correlations, what happens if you enlarge the neighborhoods? Like what breaks down?
Yeah, so this is a really good question. So why might you not, I'll skip, I have a bunch of other stuff. So why might you not want to make the locality scale as large as possible? And the reason actually is that, so effectively, why didn't we make it just arbitrarily big? And the reason is you memorize, and that's pathological. So the basic effect is that when you have too much information, you can resolve down to a single training set example, and that when you're in that memorization phase, it's really no longer kind of good, robust behavior for this thing. So this is the effect that kind of is limiting for this style of model. When you attempt to use an overly large locality scale, you get kind of pathological artifacts. So this is an example of this effect where, so on the right here, I have the outputs from like one of the diffusion models I'm studying, that's a ConvNet, and on the left I have some, or the left pair of these paired up images is an example where I've used an overly large scale throughout the entire reverse process. And one of the things that's happening is that this is becoming very pixely and very weird, and this pixelization phenomenon effectively is occurring because this model is now pathologically memorizing as opposed to doing something that's a bit more kind of general and continuous. So you really don't, there's no free lunch in terms of just scaling things up. Like you're limited by the amount of data that you have. Yeah, and cursive dimensionality is just another way of saying this. Like you can't, if you don't have enough noise, you can't use too many dimensions.
I don't see any more immediate questions, so okay, maybe one last one, and then.
Hi. Beyond visual inspection of the generated image, do you have any way to, from the activations, see that something went wrong in the generation?
You mean when you get something like...
something weird, yeah. With
yeah,
the
something
eyes.
like this? No. Yeah, I don't think... yeah, I don't think so. And I think it's a little bit of an ill-posed, or like it's a little ill-posed in general to ask the question of like, is it going wrong? We have a good, kind of prior about what a pant leg should look like, but if the model doesn't have access to kind of the platonic underlying reality of the world, then it's a little bit harder to say. I mean, whether it's doing something that is good or bad in cases where it doesn't have this kind of obvious defect, I think. So in general, I'm kind of agnostic about like what quality means, and this is part of why I said creativity as opposed to generalization a little bit. Yeah.
Thank you.
Wonderful. Let's thank Mason again.